Okay, so we drew our diagram. Here's my rock falling, and I want to know what happens right before it hits the ground. We know that the final velocity is what we're solving for because it asks how fast is it going. How fast is always v final unless I say how fast at the beginning. Time is 2 seconds, and then rest, we said in the last one, was one of our velocities. On the last problem, it was how fast was it? It stopped at the end. It came to a rest. In this case, it starts at rest, so that's vi. Okay, it's probably, you might have noticed that that's not enough information, right? All of our equations, except for this one, need 4 things, and this only works the acceleration is 0, and it's not 0 when it's in free fall. So here's the thing you need to keep in mind. For a free fall problem, A equals G, and G is negative 9.8. This is always for free fall. Now, you might be saying to yourself, well, Mr. B, why is it always negative 9.8? Here's why. Because we are always going to call down negative and up positive. So therefore, your acceleration will always be negative because the acceleration is always down. Mr. B, what if I throw it up into the air? A is still negative 9.8. Even if the object's going up, A is still negative 9.8 because the change is always down. The acceleration is always down. Okay? So it doesn't matter whether it's going down or up. A is negative 9.8. Okay? Now, a couple of super minor details. Minor detail number 1. Technically, it doesn't have to be 9.8. If it's on the moon, it's not 9.8. It's 1.62 on the moon. Don't ask me how I know that. I got weird things memorized. It's not on Jupiter. I think it's 25.1. It's not always 9.8. It's just 9.8 on Earth. So unless I tell you otherwise, it's safe to assume it's 9.8. Second thing that's minor, it is possible to decide down is positive instead of negative, and I'm fine with that. But if you do that, you need to tell me that you're switching this. I'm going to always assume down is negative and up is positive. If you don't want to do it that way, that's fine. You need to tell me. You need to tell me that down is positive and up is negative. For what it's worth, that's how I would have solved this problem normally. I would make down positive, and then this would be a positive 9.8, and I'd get a positive answer. It's not a big deal. You're going to get the same answer in the end. But if you decide to flip the direction down to be positive, up to be negative, I need to know. I need to know. So this is the way I'll assume down is negative, up is positive. So VF, T, VI, and A. Okay, VF, T, VI, and A. Here we go, Old Faithful. Now you might be saying, well, could it be one of the other ones? Sure, but if this one works, then just use it. Like, at the first equation that works, just try it and see if you can get it. So we're going to use Old Faithful here. I'll even show you the other way of doing it. I'm just going to write the equation. Remember I said you had to include the equation? If you write down which one you're using, I know which one it is. If you write Old Faithful, I know what it is. So then I plug the numbers in. So Old Faithful is VF equals VI plus A T. Okay? So VF equals 0 plus, so negative 9.8 times 2 is negative 19.6. So my final answer, VF, is negative 19.6 meters per second. Okay, 2 things to point out about how this answer makes sense. 1, it's a negative answer. That makes sense because it's going down. 2, you might have thought to yourself, hey, shouldn't that velocity be 0 if it hits the ground? We're always solving before it hits the ground, not after. Always, until next chapter. Okay? We're always solving before it hits the ground. If it hits the ground, it's a collision problem. It's not a free fall problem. This has to be before it hits the ground. So that's why my final velocity is not 0. My final velocity isn't 0 because I don't know how fast it's going right before it hits the ground, not right after. Negative 19.6 is the answer. Okay, any other questions for you here? Okay, take your time.